Oh no, I had my mic muted. Oh, that's great. Hello and welcome again. It is April 20th, Monday, another Monday. We're about a month and a half away from the end of the semester. We will have a final during finals week, which will cover everything that we've learned, a cumulative across the entire year. Well, that's because, certain things are connected in any way and you can't just avoid it. Is he playing? Well, blah. I saw it under the description of the. Wait, what? Are you sure that's what the description says? No, it doesn't. The description. Oh, whoops. I see. The category is incorrect. It should be just chatting. There. Now it's finished. Maybe it's because I want more viewers. I don't know. Now it was. That was for the Friday night stream when I played with the class of 2017 alumni. So we've been doing some alumni games. So if you become an alumni, you can join us in the alumni wars. We'll go ECR alumni versus alumni. Today we will, I don't know if you saw it, but today we'll talk about switches and fuses. This will lead us into our next mastering physics homework, which is due next Monday. And oh, thanks for the follows. Hey, it's Maddie. Welcome, Maddie. Let's see. I'm gonna pull up the fuse. Where are fuses? Short circuits. There we go. There's a slight delay, but yeah. I will open up the second mastering physics homework, which is chapter 10. It should say homework 10 or number 2 or something like that. Right after the stream, you should see it. It is due next Monday. And the other thing that we have is the combo circuits lab, which is very similar to the other two we did, and with the DC circuit kit. After that, we have our test, which is next Thursday. We're going to try our best to stick with the calendar. Yes, you copy down notes, Chris. We're going to try our best, but of course, as you know, the shoebox thing was canceled, so no shoebox project. But other than that, everything else we will do. Alright, anyway, as you can see, it says open and closed circuits. When a circuit is closed, it means all the pathways are can carry charges across them, allowing the current to flow, I should say, and which means a closed circuit is something that is on, a circuit that is on. So closed means on, whereas open means off. So closed, when a switch is closed, it means circuit is on, and then when it's open, it means it's off. Okay. So recall that the symbol for a switch is like a drawbridge, like so. So you can close this thing and drop it down. So now it looks something like this. Right. So this would indicate that the switch has been closed, allowing the current to flow, which means it is on. Oh, I have it backwards, don't I? Here, I'll try like this. So now the two sides relate to each other. So on is when it's closed, and off when it's open, right? So we have switches, and of course, sometimes what happens is that certain perhaps a piece of hair or certain dust particle or something kind of creates a new pathway in our system. And if you remember from your parallel circuit notes, whenever you create a new pathway, you actually reduce the overall resistance of the circuit. Okay, so let's take a look at an example. So here's a simple circuit with a battery, big line, small line, and then let's have some resistors. Here's a resistor, and I'll draw another one. All right, chat. What's the relationship between R1 and R2? How are they related? This is a voltage V, resistor R1. They're parallel. Good job, Chris. They're parallel. Well, so let's say this is, let's say this is your motherboard or something, or it's a very simplified motherboard. But for some reason, you might have seen on the back side there are like these little metal tabs, the soldering or something. And let's say somehow some particle got in there and created a new pathway. It's not a resistor, it's just a piece of metal or something conductive. It doesn't technically have to be metal. Other materials can be conductive. It might not be as good, but still can conduct. But comparatively, if it, theoretically, if it was a metal wire like this, comparatively between the other two, this new pathway has essentially zero resistance. This new path has zero resistance. Okay. So what does that mean? Well, that means that when the current flows out of the system, remember it comes out of the plus end, so it gushes out, and then it gets into this junction here. You can model this. Differently if you want. So that you don't see this as a sequential thing, in that it has to go through R1 first and then the new pathway and then the R2. There's no sequence to how the current will flow. It actually flows all at once. Okay, meaning if I were to redraw this circuit like this, there's the battery, and then from this battery we have our junction, and we have three pathways. One that leads to R2, one that is the new pathway with zero resistance, and another that goes through R1. Okay, so imagine that junction, that blue junction, is a fork in the road with three paths to choose from. Okay, and then here, let's try it a little nicer. So I'll draw it this way. They converge again. Alright. So that blue represents, this blue here, this blue junction, represents this entire node, this entire region. We can call it a node. A node is where all of the potential values are equal, meaning every point in this region, and I can technically extend the region all the way out to the battery if I wanted. This entire blue region has a certain potential, electric potential, but any point in this node has the same potential. So any point. Node means region with the same potential. Excuse me. And then similarly, the bottom here is also a node. Let's use a different color, purple. This entire region here at the bottom is also a node, a second node. We'll call it node 2. Meaning every point in this region also has the same electric potential. Okay, so this purple region is represented by this secondary junction here. So blue is to blue, purple is to purple. Okay. So essentially, anytime you identify a node, it's just pick a spot or a region in your circuit where there is no other circuit element. If there's no resistor in there, then it's essentially a node. And what you can do with nodes is use the squeeze theorem of nodes, similar to your squeeze theorem in calculus. We're going to squish our node into a point. Where you squish functions against each other. Here we're just going to use our pincer grip, our index finger and our thumb, to pinch this spot, and so when you pinch it, it ends up looking like this. Same thing here, when you squeeze and pinch this node number 2, squeeze it, pinch it, there we go, with your index and your thumb, and then it turns into a dot, like so. Squeeze. Squeeze. Alright, what can we do now? Well, we'll go ahead and model the current flow now using this secondary model. That might be easier to visualize. It makes it easier to visualize. As the current comes out at the plus end, remember the big line is the plus end, it gets to this point, and once you get to this point, you have 3 choices. You can take root 2, root 1, or you can take this root 0 that has 0 potential. And current always ends up taking the path of least resistance. So when you have a path that has 0 resistance, 100% of the current will go through the path with 0 resistance, and nothing will go through the other 2. Okay? And this is what we call a short circuit. I'll use black. This piece here is our short circuit. It creates a short circuit, I should say. Is a short, and this is a short circuit. Okay, this short circuit is dangerous. That's because now that we have a new pathway, all the other elements are not receiving their current, and so they don't work. If these were light bulbs, if R2 and R1 were light bulbs, then they would not receive any current and the lights won't work. Right? The other dangerous part is that, take a look at what REQ is. Okay, REQ is equal to 0. The total resistance is 0 because the other 2 resistors are turned off. The other 2 resistors are turned off. And so if I did current total, the total current in the system is equal to the total voltage in the system divided by the total resistance. This would give us V divided by 0, and if you divide by 0, you end up with infinity. Oh no, infinite current. Technically, nothing is infinite. It'll be some sort of number, but it's a lot. It's enough to kind of damage your circuitry. So when you have super high currents like this, due to the short that is developed in your system, well, it's going to start melting things. So you'll see that whenever you develop a short circuit, your electrical board or your motherboard or whatever it is will catch on fire, or it might get burnt. It'll just stop working. That's because a ton of current just tried to go through the system and it started melting things. All right. So what do you do to protect yourself? Well, what you could do is use things called circuit breakers and fuses. Circuit breakers and fuses. These are kind of like heroes that give their lives to save everyone else. The heroes we need, not the ones we may deserve, I guess. So we will use the symbol square with an F for a fuse, and we'll also use this for circuit breakers. The difference between a fuse and a circuit breaker is that a fuse is one-time use only. One-time use only. Okay. Typically, a larger fuse looks like a cylinder. You may have seen it. You may have seen like a larger. Let me fix my chair. You may have seen a larger version. It's not really a fuse, but a larger one on my desk. It looks like a giant glass cylinder. So, if you can recall, it makes noises and stuff, but mine is like a playful toy. But a real fuse is, the biggest one you may have encountered is one that's about, I don't know, a centimeter or so in size. Okay. And the sides here are coated in metal. The sides here coated in metal. And on the inside is a very thin little wire, that connects the two sides. Okay. And so based on this thin little wire, it has a certain amount of current that it can pass before it melts. So when current reaches the threshold, the maximum value of the fuse, the fuse will melt. Melts. This breaks the wire and the circuit. Okay, so what we could do is put a fuse in our system so that if we do develop a short circuit that reduces our wreck, well, the fuse will intercept our current and then it will melt, and once it melts, it breaks the connection. So what you could do is implement, let's say you put a fuse right at the front. Here, let me redraw it. Here's our circuit. Here's our fuse. Right. And then we have our three pads. I'll redraw it once again slightly differently. Now it's like a sandwich model. So of course, whenever we have this fuse, this means that an infinite amount of current is trying to pass. Whoa, infinity. What? Well, that's not going to happen. The fuse, typically fuses have certain limits. A one that is this big would potentially be, 4 amps or something. 4 amps of current can flow through. If anything more than 4 tries to go through, like infinity, well, what happens is that this tiny thin little wire that is in there will break, and when it breaks, it looks like there's a break in the road, and nothing can pass through. Nothing can pass through now. And it essentially turns off the system altogether. So it's kind of like a backup switch, except once it blows the fuse. When you blow a fuse, I'm sure you've heard that line before. I'm going to blow a fuse. So now you know what it means. It means that something happened to where a ton of current tried to pass through. Extreme Kills 08. Thanks for following. So when you blow a fuse, you have a ton of current rushing through your brain, and so your fuse is turning off the system because an infinite amount of current is trying to pass through. Okay. Now again, technically it's not infinite. There are some interesting things that we are glossing over. If you'd like to learn more, consider taking AP Physics C or becoming an electrical engineer. Right, and there are miniaturized versions of fuses. There are these little tiny ones. If you take a look at any electrical board, so if you are a PC enthusiast and you build your own PCs and stuff, you might have seen little tiny rectangles. Now these are about this, let's say 0.5 centimeters, so half a centimeter, even smaller, and there are even micro ones that are like that look like this, and they're about basically 2 millimeters. I'll just put 0.2 centimeters, which is 2 millimeters. So you can have smaller and smaller ones. On the board itself, it'll say F, or F01 or F02. That will tell you that this is fuse number 1 in your motherboard, or fuse number 2. And so if something is not working, and you're like an electrician or like a repair person, what you can do is use a multimeter, a continuity test, and kind of test if current goes through it or not. It's like a little thing that beeps. And then by touching each side of the fuse here and here with a multimeter, here's our multimeter. Okay, the multimeter will beep, 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 beep. It'll tell you that means that current can pass through here. If it doesn't beep, then you know that that little wire that's supposed to be in there is broken and no current can pass through it. All right. Now, what are circuit breakers? Well, circuit breakers are much larger. Circuit breakers. They're larger and multi-use. So I will say multi-use. Multi-use fuses. Okay. So they are slightly different. The fuse was created with a little tiny, good morning, a little tiny wire, but a circuit breaker is larger. You may have seen this in your homes, somewhere in one of the rooms, along a wall, typically 4 or 5 feet up from the ground. There's this little tiny cabinet thing. It's like a metal door or something. It's about, let's say, 1.5 feet, or I shouldn't use imperial units. It's about 18 centimeters or something like that. Is that right? No, I don't know. Wait. Let's think. No, not even close. Maybe like 25 centimeters. what is it, 18, maybe 18 inches, but 18 inches times 2.5, yeah, whoa, 45-ish. All right, 50 centimeters, 50. It's like a little door. Mine has like a little slider thing, a slider lock where you have to press on it, push on it, and then it opens up. And once you open it up, so here it is, all opened up. So this is like a door that opens up. Okay, so here's our wall. And inside of this little cabinet thing, you'll see a bunch of rows of circuit breakers. And every one of them has a little label on it. So mine are all oriented sideways. It is possible that it could be vertically oriented, but typically the sideways ones are much more common. Okay, and you'll see like one of them is like the garage, or one of them is like the kitchen, living room, and so on. It could be, you know, bedroom number 1. It could be just your room. So you may have noticed that sometimes when you're pulling too much current, so let's say you have your computer on and you're doing your gaming, and you have your, you know, TV on, you have your music on, bunch of lights on, LEDs, and well, actually LEDs are pretty efficient, but it's traditional light bulbs on, and someone busts out their hair dryer at the same time. Hair dryers actually pull a lot of current, right? And you'll notice that hair dryers themselves have a little fuse box too, so they have like a little red button or something, and sometimes that thing pops out, and you have to press it again to use the hair dryer again. That's because it's protecting it from pulling a bunch of current. So what is it? Well, now imagine on a circuit level. Let's take a look at on the circuit level. So imagine this being your power source. Of course, your power source would be AC current, and it's a different symbol, but we'll just pretend we have DC power for now. So instead of a little square with an F, of course in circuit symbols you would still use square with an F, but I'm going to try to draw a realistic circuit in that this is our power source as much as possible, and then here are our pathways, and all the outlets in your homes are a bunch of parallel rows. They're all, you know, I should draw it this way. So as you can see, they're a bunch of open parallel rows. So these are all the outlets. I'll just draw 5. That's good enough. And then it goes back to the bottom. Okay, so what is this trying to show? Well, imagine trying to plug something in. So here's your plug. You know how it has like 2 little feet, or 2 little teeth? And so when you plug something in, plug it in, what you're doing is you're finishing one of the connections. So the current can flow, so as it comes into this junction, it will flow. Now with these gaps, the outlets that are not being used, nothing flows through them. But if you do plug something in, it'll go up one of the teeth, it'll go into the system, and then the other way it'll come back. So if you ever actually cut one of the wires, you'll see that there are 2 wires inside, at least 2. So it goes up one teeth, down the other, and it finishes the circuit, right? Well, what do we have here? In front we have our box, our bunch of sliders. So a circuit breaker is a big giant piece of metal, and normally this giant piece of metal, I'll put C.B, circuit breaker. This giant piece of metal connects our circuit similar to a switch, where it's a drawbridge, And so this giant piece of metal just connects our circuit and everything is fine and dandy. You'll see that all of the sliders are positioned to one side. So this is your room, your room. So this first one here on the top left is the circuit breaker for your room, right? So everything is normal on a normal day. It's on the same side typically. Okay. So when you pull too much current and a ton of current tries to go through, okay, this will start heating up the circuit breaker. Circuit breaker heats up when too much current flows. I mean, it is all technically always heating up. Of course, over time, it'll just keep getting hotter and hotter. So even if you don't use too much, you're using normal amounts, but for a very long time, that could potentially have similar effects. So sometimes you might just blow the circuit breaker, and it's like, hey, what happened? All of the current in my room doesn't work, but my sibling, my sister's room is fine. Oh no. When too much current passes through or goes through the circuit breaker. Through the circuit breaker. Circuit breaker heats up when too much current runs through the circuit breaker. Okay. So what happens to metals when they heat up? Our expert chemistry students will know. Is Maddie still here? Maddie, what happens? Oh, the other Maddie from period 5. What happens to metals when they heat up? What happens to metals when they heat up? If you'd like to learn more, consider taking AP Chemistry next year. Well, maybe they get hot. They expand. Very good, Maddie. Well, so as it gets hot, it expands. It means it elongates or it gets bigger. Okay. So when it does get bigger, it gets too big for it to fit inside our system, inside our circuit. So when it's too hot, let's redraw this. Here's our battery. This is where the circuit breaker is supposed to be, but now it's too hot. Let's connect 2 of them or 3 of them. So this would, or I guess 4 of them. This will tell you that we're using a bunch of stuff. Alright, so now the circuit breaker is too hot, so it's too long, too big to fit in there. And it pops out like this. Kind of like a switch, it pops out. And now that it pops out, well, the pathway is open, right? This system is now open, and open means it is off. So now no current can go into your room, and now you can't use any of your devices. So what do you do? Well, if you run to the little circuit breaker cabinet thing, and you could try to slide it. So you'll see that one of your sliders. So this, let me see if I can erase. Oh no, oh too late. So you'll see that your slider is probably like all the way out here or something, and it's not in its regular position. So you might rush there and try to like slide it over to the other side. And when you're sliding it over, it's what you're doing is you're applying force to push. You're doing an applied force, and you're forcing it to get in there, to get and squeeze inside here. But if it's too hot and too long, well, it's not going to fit. So sometimes if you do it too quickly, you can't get the system to turn on again. So you have to wait. So typically if you blow a fuse in your home, Remember, the fuses in your home are circuit breakers, and they're multi-use. They're not single-use, thankfully. If you do blow a circuit breaker, just wait like 5 minutes. Wait 5 minutes. Let it cool down. Maybe let your brain cool down because you've been using too much current. Wait 5 minutes, let it cool down, and then try to go to the circuit breaker closet and and then check the slider. I'm sure one of the slide, if it's not labeled, usually they're labeled, mine are labeled. If they're not labeled, just one of them is probably not like the others, and so slide it in, and you'll see that you have restored power. All right. So now if a circuit breaker goes off in your homes, you are the one that can save everyone's day. You can rush to the circuit breaker closet. Now, of course, you have to figure out where it is. It's probably in someone's bedroom. So figure out where it is, and you'll see, someone is using too much current. Give them a timeout. Tell them to stand in a corner for 5 minutes, and then turn on their circuit breaker. All right. So using all of this, we can start modeling some more difficult questions. This is actually so cool. Oh, thanks, Dennis. You can start modeling some more complex circuits. So we will start using circuit breakers and fuses inside of our circuits to analyze, see what we can do with it. Dennis, do you have a circuit breaker in your room? Well, for the entire home, for the entire complex, it'll be one box. So not everyone has, not everyone has it in their room. So it's just in one room. Yeah. So Dennis has it in his garage. So it's just one box. Yeah. All right. You have one Chipito. Very cool. Very cool. So you're the go-to person. So you can charge a premium. you want your electricity, your current back. That'll be $5 to fix it. All right. All right. I suppose that is it. For circuit breakers and fuses. We can model fuses and other stuff in our theoretical problems using switches instead. So let's do a quick example. Let's say we have a power source, a battery here. We have resistor. We have one pathway that has a switch. And another pathway that has a resistor. So we have R1, R2 here, and R3. So these are all variables. V. Okay. In part 1, switch is off. So I should say switch is open, which means it's off. Okay. Now, if I have the switch in this system here, in this circuit, this switch only closes and opens one of the pathways. It doesn't close or open the entire circuit. Right. So when it's off, let's use purple. Current when it's whoops. Part 1, not I. Part. Well, that is kind of confusing. So this is part 1. In part 1, switch is open, and this will be the current. I when off, when switch is off, I should say. When switch is off. So when the switch is off, we can see that the current will come out of the battery. It'll go through this resistor. Now it has a choice. It could either go through this pathway with the switch or the resistor. Now when it's off, an off switch is like a resistor with infinite resistance. So switch off equals infinite resistance. Infinite resistance. So R equal to infinity. So now you have a choice. Do you want to go through R2 or do you want to go through R infinity? Essentially, R infinity means you're not going through. So when the switch is off, nothing goes through it. However, there is a pathway for us to take, and so after going through the resistor number 1, you'll go through resistor 2 and then through resistor 3, and you're down to the battery. Now again, even though I said after resistor 1, remember there is no sequential order. There is no R1, R2, and then R3, as if, the charges, that one singular charge goes through one resistor at a time. Remember, the entire system turns on all at once, all at the same time. Is there a delay? Yeah, there is a delay in the signal. That's called transmission speeds. Consider taking AP Physics C to learn more about transmissions. But for all intents and purposes, when one charge gets pushed to move through this resistor, that causes a domino effect, meaning there is a charge here already. And so when this one here, this dark circled one, moves through, it pushes this one here, this hollow circle, to move one, and that pushes the next one, and so on. And you can see like a domino effect. In order for this dark blue one to move forward, okay, the one in front of it has to move forward, and this causes a chain reaction throughout the entire system all at once. Okay, so that's why there is no sequential order. Everything happens at the same time. So when the switch is open and the pathway is closed, if the pathway is open, nothing can flow through the switch, and so we are forced to go through all 3 resistors. Our resistance rec is equal to, of course, R1, 2, and 3 are all in series, so the total resistance is R1 plus R2 plus R3. We can add them because they're in series. All right, let's do part 2. Part 2, switch is now closed. And when it's closed, it means it's on. Right, so let's redraw it. Here's our battery, here's our resistor 1, and now the switch is closed. So that means we drop the drawbridge like so. This is R1, this was R3, and R2 is over here. Now you can see how this pathway with the switch is parallel to the resistor 2, and the total resistance is actually 0. So when the switch is closed, the switch on, I should say, switch on equals 0 resistance. R equals 0. Okay. So let's draw our current flow diagram. Here's the current. I'll do it in red. Current I when switch is on. So when the switch is on, we have a pathway that we can take. So out of the battery, out through resistor 1, we have now a choice. We can go through the 0 resistance or we can go through R2. Of course, similar to a short circuit, the switch acts like a short circuit in this system now, we will definitely send all of our current 100%, and nothing goes through the other pathway. When you have a choice between a short circuit, like a switch in this case, or a resistor, the choice is pretty simple. You go through the zero resistance pathway. And now we go through R3 and we're done. So nothing goes through. That means if R2 was a light bulb, it would be turned off because of this short circuit pathway. What is the total resistance? Chat, now that we have our switch closed, what is the total resistance in our system? While I drink some water. There we go. We got one. Tard guard. It is now just R1 plus R3. Okay, R2 is turned off, meaning since no current goes through R2, it's basically like not having it in the system in the first place. Okay, so it has no function. It doesn't add any resistance to the system. All right. Well, that's it for today. Thank you for tuning in. I will now open up Mastering Physics number 2, so check that in like a minute or so, and then you can get started. It is due next Monday. See you later.